Okay, let's roll on to the next section here. In section 2, we start looking at the basics here, the foundation of what this course is going to be all about: voltage, current, and resistance. And in doing so, they become the building blocks of everything that we're going to do for the rest of the semester. So you need to make sure that you understand the underlying principles, which are going to be given to you in this chapter, and then the ways that we use these constructs or values of voltage, current, and resistance to learn how to do our circuit analysis, and it's understanding the difference between the way the electronic and electrical principles work for each of these measures. So the underlying principles and things that we need to gain an understanding from are those things that are very, very basic. The atomic structure, what is an electrical charge, and then looking at voltage, current, and resistance, a simple electric circuit, and basic circuit measurements. And then we're going to spend a considerable amount of time on this last section of electrical safety. Although in this online class, electrical safety is not of paramount interest. When you are in the lab, these things become very, very important for you. So we're going to look at, to start with, the definition and describing atoms, the concept of charge, defining voltage, current, and resistance and their characteristics, as well as their units of measures, describing a basic electric circuit, what it takes to make a basic electric circuit, and then, as I said before, looking at the hazards and safety practices that we need to adhere to. An extensive list of key terms: atoms, electrons, free electrons, are all basic. We're going to spend a few slides looking at those, and then looking at the difference between conductors, semiconductors, inductors, charge. Again, we're going to catch every one of these terms as we go along, and we will start to define them. You need to become familiar with each of these terms and how you delineate and describe each one. The important ones, again, being voltage, current, and resistance, and understanding what the physical property is that we're talking about when we talk about each of those key characteristics. So the section objectives, then, describing what's an atom, what it's made up of: nucleus, proton, neutron, electron. Understanding fundamentally what an atomic number is, looking at a model that we call the shell, and how they were built, to try to understand what's going on at this subatomic level. So as we look at this, first off, we need to define what is an atom. An atom is the smallest particle of an element that retains the characteristic of that element. So if we could chop a piece of copper down into its smallest piece, it would be an atom. And that one atom would have the characteristic of the element copper and retain every bit of it. If you look at the periodic table, there are 109 elements. Some of them are defined, some of them are not defined. Most of them are. So we're going to look at and try to understand what's going on with an element by applying something called the classic Bohr model. And in the classic Bohr model, it's much like what we've used to understand our solar system. So on a macro scale, we've got something like a solar system. On a micro or super micro scale, we've got the Bohr model, or this planetary type structure where we have electrons whizzing around, neutrons and protons at the center. And this characteristic of the atom then is really a big balancing act, so that everything stays in place. As long as everything behaves, this is the way it looks. If things don't behave, then we've got something else going on, and sometimes it can be catastrophic. So if we look at then the arrangements here, elements are arranged then in the periodic table by an atomic number. Atomic numbers then equal the number of protons in the nucleus. So if we look at the simplest, the hydrogen atom, and the next one up, the helium atom, you can see in the hydrogen atom we have it identified as atomic number 1. The helium atom has atomic number 2. And relating that specifically to the protons and neutrons, you can see in the model on the bottom, we have 1 proton, no neutrons, and 1 electron. If we look at helium, though, we've got 2 protons, 2 neutrons, and 2 electrons whizzing around the nucleus there. The interesting to think about with atoms is that it's quite a magic act here. You'll notice that the arrangement of the orbits, there's more air or more space in between the neutrons, protons, and the electrons than there is solid matter. So everything around you is playing this magic act of acting like a solid when really there's less about it. I said before, if things started misbehaving, we would have catastrophic events happening. As long as everything behaves, you've got solid material that you start describing by these models. So if we look at electron shells and orbits, electrons orbit the nucleus at a certain distance, and this is how they maintain their balance, and it's all based on the charge between each of these subatomic particles. Electrons near the nucleus have less energy than those that are further out. The orbits then are discrete. That means they're separate and distinct. We start looking at the energy levels between each of those orbits, and each orbit then has a corresponding energy level. The shells then describe the orbits that are grouped into these energy bands, and we designate them shell 1, shell 2, shell 3, and it just depends on how many electrons we've got and what element that we are specifically talking about. The valence electron is always the outermost shell of the element. So you can see here in this model we saw before, where we had lots of protons and neutrons in the middle. Out here on the utmost or the furthest out, we have our valence electrons. Electrons in this shell then are called valence electrons. They're further from the nucleus and less tightly bound to the atom. We're going to find out later, this is the characteristic that gives us current flow. Those valence electrons are allowed to jump from outer shell to outer shell as they move along the path of current. Valence electrons then contribute to chemical reactions then and bonding. They also determine a material's electrical properties. Valence electrons can easily jump to higher orbits within a valence shell. Another process that we need to understand is something called ionization, creating ions. The process of losing a valence electron is the process of ionization. The escaped valence electron then is called a free electron. The resulting positively charged atom then becomes a positive atom. So as soon as we lose an electron, that particular atom becomes more positively charged, and we call it a positive ion. For hydrogen then, the symbol becomes H with a little plus in a superscript next to the letter. In contrast then, a negatively charged atom will have an H with a little superscripted negative sign. If it gains an electron, it becomes more negatively charged. So if we look at a copper atom, we're going to use copper a lot in the study of electronics, so we might as well get used to looking at this. The number of electrons in each shell follows a predictable pattern according to the formula 2 times n, the number, squared. So we can see here, off to the left here, first shell, second shell, third shell, fourth shell, and in this case we have 2 electrons, 8 electrons, 18 electrons. Those numbers obey this formula, 2n squared. Okay, so we can see here in the Bohr model, 1 electron in the fourth shell, 18 electrons in the third shell, 8 electrons in the second shell, 2 electrons in the first shell, and then we have a total number of 29 protons in the nucleus. Free electrons then make copper an excellent conductor and make electrical currents possible. So this is the whole process that occurs every time we hook a wire to a battery and a light bulb and we see the light bulb light up. We're going to start giving up electrons, which form the current flow for a simple circuit. So from that, then we need to look at and understand what characteristics then are formed by what we just looked at to make good conductors, good semiconductors, and good insulators. You can see we've got a spectrum here. Good insulators are poor conductors. Poor conductors are good insulators. So a lot of this may be intuitive to you. What makes a good conductor? Well, elements like copper, silver, and gold make good conductors. They readily allow current to flow because the free electrons are allowed to move. In a semiconductor, it takes a little bit of coaxing to get the free electrons to move about. In materials like silicone and germanium, we have to do things like doping to try to get those free electrons to move a little more easily, but it takes a lot of controlled applications. And then finally, the insulators, wood, plastic, rubber, ceramic, glass, these guys don't like to give up anything. They are rock solid. So they're considered poor conductors of electric current. Okay, so we've looked at very quickly and simply what the atomic review is, with the idea that from the atom, we wanted to get to what makes up a good conductor, semiconductor, and insulator. So all of these basic things really apply to those three types of materials that allow us to build circuits and electrons to flow. Okay, so in the next section we're going to look at electrical charge. What does electrical charge really mean? What does it take for a positive charge and a negative charge to occur? So when we come back, we'll pick up with electrical charge introduction.